Welcome to our fall seminar series. We're going to do this jointly with the Center for Land Use Efficiency and my unit, the Statistical Consulting Unit. This series of seminars is a result of a conversation that Mike Dukes and I had earlier this summer. And so we decided to put together this series of talks usually the first Friday of the month, culminating with a personal visit by Dr. Hans-Peter Pifo from the University of Hohenheim in Stuttgart, Germany. Here, that's kind of the capstone talk. He's going to be talking about Bayesian approach to designing fertilizer trials. My talk covers the basics, and just right off the bat, what this seminar is not about is trials where you have where fertilizer rate or any other rate. What we're talking about really replies to a lot of rate studies, is not the main focus. For example, if you had it evaluated in turf grass cultivar and you're doing under low and high end rates, or you have a fertilizer rate as a secondary factor in phytopathology studies. What we want to do is we really want to foster best management practices when it comes to such trials. And that includes agronomic practices like site selection, plot size, blocking, but also the statistical consideration, in particular the rates to deploy and the number and the range of the rates. And then not to miss out on the interpretation of such studies. Want to point out common mistakes when you conduct such trials. One of them is that bigger is almost better. There are people who are really in love with on-farm trials and they think it's the best thing since sliced bread. And the only valid answers you can get is from an on-farm trial. Well, on-farm trials have limitations. For example, often the producer will not let you put out a zero rate because we don't do that. And if you, for example, think of corn and nitrogen, if you don't put any nitrogen out, you know what you're getting, and that's nothing. The other thing is that you pick rates that confirm your personal bias. So you've already made a conclusion right before you start the experiment what that best rate should be. Other one is not taking covariates when they might help you interpret the results. A written protocol actually doesn't only apply to this study, but it applies to any kind of study you do. If it involves more people, you really need to have a written protocol. And that ensures that everyone is on the same page. And that specifies a lot of in detail what needs to be done. And then really participants should sign off on the protocol so they can be held accountable. I've been involved in studies where that wasn't the case, and the results were rather predictable in that a lot of things didn't happen. Let's break this whole process down in steps. And the first step is defining the objective. Really, it's a no-brainer, really, but it's often overlooked and it's really not codified, those objectives, what you really want to do it. Key is the objectives, that's a prerogative and the responsibility of the lead researcher. Nobody else is going to do it for you. And the objective, of course, depend on the crop and economically valuable crop partners. It could be that you're going for maximum agronomic yield. more often than nowadays, we'll define that in terms of the maximum economic yield. And that is where the third talk, the third talk will be all about. Or you could use look at use efficiency, or it could be minimizing environmental impact, or you want to study the effect of rate and timing, or crop quality for whatever crop you're working with, if that's an important consideration. Then comes the selection of the trial site. Site uniformity is important. The goal is to reduce the variability in trial results. You want to reduce the residual variation, and the smaller the residual variation is, the more precise is your experiment. That means you want to characterize a site by soil texture, organic matter, pH, residual soil nutrient levels, whatever have you. A big issue is that people tend to believe that when you have a trial site, you divide it in the blocks have to be contiguous, and the blocks have to be rectangular. Nothing could be further from the truth. No matter what experiment design textbook you open, you will never find it. Yet those myths persist. If you have the option, you can actually construct blocks based on prior information. Key is that you want to plan. You want to know, have an idea what the variability is. And if you fail to plan, if you fail to plan, is planning to fail, as the old adage goes. You really need more than a single environment, because a single trial is just a snapshot. It's no different than having a box of marbles. You grab a handful, and you look at the color distribution. You need more. And with the marbles, you can see the more you sample, the better idea you have of the distribution of the colors in that box. Yet, when it comes to field trials, we assume that, well, not assume necessarily, but we kind of imply that this single trial is everything we ever need to know. And of course, if you're trying to develop with rate studies, develop recommendations for a particular reason, obviously you want to sample that region. Now, some people are reusing the same site and randomization even for an annual crop. That has implications, because you are now no longer have independent residuals. They are correlated. Now, if you are, for example, on a sandy site like Hastings, there probably is very little carryover from one year to the next. You just have to be aware of that, of the implications. Now, if you have a perennial crop like a forage grass or fruit trees, then you're automatically in a repeated measures situation. Important here is for rate trials is rate is treated as a quantitative variable. You are in a regression mode, not in a classification mode. And the objective is we just want to find out how the response changed in Y changes with every unit change in X. So we are as I mentioned, we are in a regression environment. Regression does not imply a straight line relationship. Okay? Regression is just modeling the independent variable as a quantitative factor. Now, rate study, I would say a minimum you need 5 rates. And the center of that rate is, you can call it a recommended rate or current agronomic practice. And then you want to step above that, and you want to step way above that. And that enables you to determine the shape of the response curve. And then you want to have a low rate and the control rate. And what happens when you omit that control or the zero rate, that has implications for the estimation, for example, of the economically optimal rate. And that's what our third speaker is going to talk about. Alex is a graduate student at Iowa State, and he will do that in November. Randomization. Everything we do in statistics is based on the assumption that treatments will have been randomly assigned to experimental units. And that's done because we want to avoid bias. Now, most experiments that we conduct were probably done as randomized complete block designs, meaning every block contains every treatment. And commonly 3 to 4 blocks, but there's no magic to it. But important is that the randomization is done independently for each site and block. So you don't use one randomization and apply it to all your trials. The second condition of a valid experiment is replication. For that, you will need to know 2 definitions. And students who have taken my class over the years get tired of me re-emphasizing that over and over again. The experimental unit is the smallest unit to which a treatment is applied independently. So having a plot, splitting it after you've applied a treatment, that's not replication, that's pseudo-replication. The experimental error is the variance among experimental units treated alike. Implied here is that, of course, you need at least 2 replicates or 2 blocks. Plot dimensions. Preference is to keep it as small as possible. The reason simply is you have less variation within a block. So your plots tend to be more uniform in a block. However, that's really the plot dimension depend on the crop and the fertilizer application method. If you have a fertilizer spreader, that if you can calculate it, that has a 20-foot width to spread it, your plots have to be that wide. Plot length depends often on the harvest equipment. So if you have using a potato digger, you will need longer plots. And you will need much longer plots, like using a small grain combine in a small grain trial, where you can have 10-foot plots. That's plenty to harvest with a plot combine. You may need buffer rows. So if you have a crop like potato or corn, you have maybe 8 rows or so in a plot. Then you harvest the center 4 and use the outside rows and as a buffer. That may be due because you may have leaching or lateral transfer of nutrients from one plot to the other. Could also be that you have shading effects, so an effect of crop height in response to applied fertilizer. But that's where your subject-specific knowledge applies. You know what to expect. I was a forage breeder for the first 30 years of my academic career, and we always surrounded the entire trial with a buffer row, so we could keep the integrity of the entire experiment. Plot labeling, which is a really sore issue with me. Everybody uses plot ID, yet magically that information tends to disappear from the time the data is taken till the data wind up on my desk. Yet it's very important because you can look at the spatial distribution. If you have the plot ID information, you can look at the spatial distribution of your residuals. Do you have gradients in your experiment? That's why it's important. Everyone has this information, and so it should stay with the data. And obviously, the data should be taken by physical unit. Often we have the problem, we like to do something, and then we discover we just don't have enough field space. Right? You could drop an entire rate completely, but if you have 5 rates and you drop 4 and you drop 1, then you only have 4 rates, and that's rather marginal. You could reduce the number of blocks. Yes, you can do that, and that would be preferable to dropping a complete level. Or you can work with incomplete block designs. Now, when you do that, it's just not haphazardly dropping one block. You can use optimality criterion to design the trial. And Dr. Pifo is going to talk about that in December. In particular, his approach is going to be looking at a Bayesian approach. And the whole idea about Bayesian is to incorporate prior information into the current trial and then updating results with the results from the current trial. Then you get ready to apply rates. Often forgotten is that experimental conduct affects precision. In the past, I used to say that errors do not cancel out because you have a variance. Terms on variance is a quadratic, so they will never, errors will never cancel out. So when it comes to experimental conduct, I would say that consistency is almost divine. And for the note to the graduate students, if we have some in the audience, nothing beats showing up in person at critical times. Plain reason is nobody has a more vested interest in the outcome of your experiment than you. Not even your advisor, certainly not your temporary helpers. So act accordingly. When we apply rates, we often use machinery to do that. They have to be calculated. And for example, if you have a spreader, you need to calculate the ground speed. Can you have a consistent enough ground speed that you are actually applying the rates that you claim to have applied? Same applies if you have irrigation and you're using injectors. They also need to be calibrated. Third point is application timing. If you have for example, pre-plant and planting, those are fairly easy to accomplish. But then if you have growth stage repair dependent application, they have to be applied at that growth stage. And that means also you have to monitor your growth stage. Once you've done all that, your experiment is ground, you have applied your fertilizer, then it's time to gather data. And obviously the data that you take should be commensurate with the objective of the experiment. Important thing, sloppiness, and I know this is a harsh term, has no business being there, or being less than careful taking data also has no business. And again, here, this showing up in person for the graduate student. There are things that can help you, and that is preparing data sheets, and I use that term in the broad sense. So it could be electronic or paper beforehand, that you know what goes in what slots, and essentially taking the data becomes an exercise in making sure that every slot has a number or whatever in it. And having templates to do that will help you in the next step. My advisor, Mike Kassler from the University of Wisconsin, he was probably the most diligent about this. In fact, when he put an experiment in the ground, he already knew what the paper was going to look like. And then he worked his way back and say, what do I need to do at this step that will make my next step easier? And a colleague of mine, Harold Walker at Auburn, talked about the pay me now or pay me later approach. You can put the time in developing a consistent way of entering the data, or you have to figure it out later. A lot of times our data are time sensitive. So the interval has to match with what you're trying to do. For example, if you have a plant pathology experiment and you want to calculate the area under the disease progress curve, then the rating, the interval between the rating has to be short enough that you can make a curve that's sensible. Or if you look at working with small grains and you want to know the developmental, the days it takes a crop to get to that particular stage, you have to monitor the crop at short enough intervals that the data actually make sense. So all that means is that you have to monitor plant development. Expand a little bit on that is all data is recorded and on a plot basis, referenced by a plot number, however that is. That doesn't have to be numeric. It could be like the British postal code. It could be a number, a letter combination, but although numbers are much easier to do that. And the way you number your plots makes certain things easier. If you number your plots on a grid, then you can easily find your way, and you can monitor and you can model the residuals, for example, in a spatially dependent way. Again, monitor plant development. You can take, often we take ancillary information, chlorophyll content, NVDI, or leaf area index, or plant height, biomass accumulation, where we sample repeatedly over time. Question is, do you need soil sampling during critical point during the season? If it is, then you have to do it. It didn't have time is not really a valid argument for those kind of studies. Then you do crop yield and quality related measurements, and it's simple. It's as simple as knowing the area that you harvest. Do you need soil and tissue analysis? So that way you have to sample the tissue over time, and the sensitivity of that analysis should be in line with your objectives. Often we use a commercial lab for that, but you may want to look into how they process the sample. Because the commercial labs, they are used for, their money comes from farming, from dealers and so on, and their requirements as far as precision and accuracy is not what we need in research. Now we come to the data analysis. Over the last, I've been doing consulting now for a better part of 30 years. I developed this structured approach to data analysis. I used to call it my 7-step approach. Now I call it my traffic light model. And you can see these are European traffic lights because they have a yellow phase between red and green. The red is the stuff that you absolutely need to do before you proceed. If you don't do it, the rest of it doesn't matter. Now, the green is where you want to be. You are kind of want to know, did I have something? Was there something there? And I want to interpret the data. But this is absolutely essential to do that. Then the second part in yellow is getting a feel for the data. And you can do that by graphical means, and not assessing your data graphically before the analysis is like jumping into a lake without knowing how deep it is. You may be lucky, or if not, you wind up with a broken neck. So you want to plot the data. You can also do it in tabular form. And SAS has this nice procedure, tabulate for it. R has a similar function that was retrofitted from R. JUMP has the same thing. Know what to do. The minimum and maximum values, for example, make sense. And you are the expert on that. So if you calculate corn yields and you have 500 bushel per acre corn yield, it might be possible, but it's not likely. And this first approach can tell you, are there unusual observations? I do not call those observations outliers. Outliers have only, to me, a meaning in the context of a statistical model. These are unusual observations. Often, these unusual explanations can be explained what one of my Brazilian students called a finger error. So you just make a data entry mistake, a decimal point got shifted. Then you fit, even though we are in a regression model, we initially fit a classification model because it allows us to look at easily to look at the residuals. And the residuals, no matter what software you use, you should in fact inspect the residual plot. And then ideally, it should be just a cloud without any pattern. Here you can clearly see outliers. And when you look at these plots, they usually plot the studentized or normalized residuals against the predicted values. Then you can see you have a chance, does the outlier increase with the predicted value? It means there's a relationship there. You have to model that. Are there extreme residuals? And I use as my cutoff point, I use a standardized residual greater than 5. You can isolate it, look at that observation and say, okay, how did this happen? Can we have an explanation? Is it just simply a matter of having a decimal point entered wrong? So if you can identify the reason for the outliers, sometimes we can't. And then we just drop that particular observation, but always noting our criteria. But it's important, particularly important when you publish the data, that you want to give the reviewer and the reader an idea, okay, we dropped this observation because of this criteria. And then if there is a pattern, we can model the residual variance. For example, if you have count data, then you often see that, but count data are not normally distributed. So you can use a generalized linear mix model. And then you want ahead and model the regression relationship. This table here is kind of gives a comparison between dealing with qualitative and with quantitative factors. And in qualitative factors we generally have only a few levels, whereas with quantitative levels we have more levels. The objective here for the qualitative factors, I would call that damage assessment. When we have in a regression environment, we really want to do prediction. And so here we're using traditional ANOVA or class techniques. Here we're using regression techniques. And generally for class models, we use the approach, analyze them as you randomize them. That means we don't drop effects. When we go to regression, we often want to develop the most parsimonious model. What's common to both is we use least squares techniques to do that. And nowadays, more often than not, we use restricted maximum likelihood to estimate the random effect, because REML techniques enable us to model the residuals. If you do least squares techniques for the random effects, you don't have that option. And yeah, we can combine, we can have a quantitative factor added to a class experiment, and this would fall under the heading of analysis of covariance. For example, we may want to use a number of plants per unit area as a covariance, but that's strictly to reduce the residual error, make more precise estimate. When we combine a quantitative factor with qualitative factor, we are in the realm what's called multi-source regression. So we are fitting a regression model and then adding classification variables to it. Now, when it comes to modeling, it's important to remember what George Box said is all models are wrong, but some are useful. And models are there to help us make sense of the data. That's not the reality. It's just our interpretation of the data. And data is a key word. If you've emailed me or received an email from me, I have my byline, email byline, "In God we trust, all others need to bring data." Okay? What you don't want to do is approach a regression models with a preconceived notion. For example, I said the response has a second order or a quadratic response. That's the only one I will consider. No, let the data tell you what's here. That's why we do an experiment. Now, we've been in this business long enough that we have there's a body of literature that can kind of inform us what are likely models. But models change over time. You can't act like that everything you ever needed to know you learned in graduate school. And I apologize to Robert Fogel. And those of you old enough know my reference. It's to everything I ever needed to know I learned in kindergarten. Important is that linear does not mean straight line. A simple linear regression, that's SLR, is a linear model. A quadratic is a linear model, so is a cubic. The way you determine that is simply as you take this first derivative of the prediction equation. If that depends on the parameter, if it doesn't depend on the parameter, you have a linear model. If it does, it's a nonlinear model. So when you see here, if you take the first derivative, it does not depend on a parameter. That's a linear model. If you have an e to the something term in here, if you take the derivative, it depends on a parameter. It's a nonlinear model. And I'm going to give you the reference to this book later on at the end. So we have simple models. We can use ordinary least squares. We can use a linear model. So we have beta naught, your intercept, and beta 1x. So x is your quantitative variable, and this is the rate constant. You can have a quadratic relationship where we have a linear and a quadratic function. They are simple. For example, here, an experiment, the data come from Douglas Zodarelli. And so we have here the total yield for potato and the marketable yield potato. And the yield is in hundredweight per acre, which is a standard way of expressing yield in potato studies. So you have to look at the x-axis at the scale that's presented here. And so what we have here is a strict straight line relationship. There is no hint of any curvature in there. And what we can see here is that what this tells us that every additional pound of increase will get us 26 pounds increase in yield. Every pound increase in P2O5. So this is where you have a straight line relationship. And as befits Dr. Zodarelli's study, he likes to use these kind of rates, 6 rates. And so that's very nice. Another study here. This is from another paper. I don't know where it came from. Nitrogen rate, pounds per acre, and then the yield here. Okay. It looks like we have a quadratic relationship. But if you look here, is the quadratic component is very small, and the confidence interval is includes 0. In other words, we can't really tell whether or not this the quadratic component is different from 0. So we could have competing models here. We can have a linear and a quadratic. We can look at the coefficient of determination, R squared. We can look at the penalized fit statistics, and we can also look at the confidence intervals for the parameters. And I also already told you here that that confidence limit does not include 0. Now, when we have a quadratic model, of course, we can calculate the maximum yield, and the maximum yield here is close to 400 pounds. But now look at the confidence interval for that maximum yield with the inverse prediction. It ranges from 207, which is here, to 576. That range is so huge that it's useless. Okay? Question then, does this study have enough rates? I think you'll agree with me that it didn't. In particular, what happens here is in this study, they doubled the rate when they probably would have been better off inserting a rate and even adding another higher rate to it. Now, can you just get away with 3 rates? And it's done. It's also done at UF. Okay? So let's start with a study where we have rate 1 and rate 2. And you know the old saying, the shortest distance between 2 points is a straight line. So you have a linear effect. We are defining this point here on the y-axis as m and m plus d. So that is the difference here is d. Okay. Now let's assume that this straight line relationship meets our standard being statistically meaningful at 0.05. So now let's add a third rate to this and put that third rate intermediate between the highest and lowest rate. Again, now we can actually have 2 contrasts, one for the linear and one from the deviation linear. Question is, how big of a yield difference or whatever response variable difference do we need to have in order to detect a deviation from linearity? And this is where you will be pleasantly surprised that algebra is actually useful beyond college and high school. So when we do this, develop the linear contrast, it's just minus 101. And for the deviation, if the rates are equally spaced as 1 minus 2, 1, multiply the coefficients, and the sum of the product is 0, meaning we have bona fide contrast. The sum of squares for our linear is determined by b times d squared over 2. And the sum of squares for the deviation is b times d minus 2c squared divided by 6. And the b here is the number of replicates. So that actually cancels out. Question is, what we wanted to know is, when is the sum of squares for the deviation equal to the sum of squares for the linear? Because if it is, then we can say we have a statistically meaningful deviation from linearity. Well, you set these two equal, you solve for c, and the result is that the c is either 30% below or 36% below that range determined by the original range, or 36% above that. That means really, first of all, here, this is based on a nice little paper by Pierce. It's quite old, but quite revealing. So C must be substantially smaller or larger than the range between rates 1 and 2. Take-home message here is that experiments designed to detect a linear effect do not have nearly enough power to detect deviations from linearity. Now, this does not mean that you're throwing money or replicates at the problem. you're better off thinking about how you might deal with that problem. Well, before we go back, let's talk about models if we have enough rates. One of them, and these are now with nonlinear estimation methods. We can have a linear plateau model. We have a linear increase in the response, and at one point there's just random variation. We call this point here A is a joint point, and there's no further increase in yield. If there is an increase in yield or whatever response is, we have a linear slope model. If we have enough rates, we can actually have a linear slope and a plateau model. Or quite popular is this quadratic plateau model. We are not assuming a linear but a quadratic increase till the plateau, and then no further increase. And this is often the model that's used for economically optimal rates. So let's look at a linear plateau model. You've seen this data before, and here we have the rate constant, and then here at a rate of 248 pounds per acre of N, there is no further change. And so this is a joint point here, and this joint point is based on the data. It's not a swag that you do it visually. The data will tell us where that joint point is. And so there's above here, there's no further improvement. Now, look at the confidence interval for this joint point for the inverse prediction. It ranges from 158 to 338. It is smaller than for the optimum and the quadratic, but it's still quite large to really serve our purpose. Again, did the study have enough rates? No, because you're operating here somewhere in no man's land here. It would have been, for this kind of model, would have been much better to have a rate close to 300 in this study. Now there's one true nonlinear model I want to introduce is the Michalik, what's known as the Michalik yield equation, or otherwise known as a law of diminishing returns. What that tells you is that for every additional unit of input, you get a smaller and smaller response until you get to the asymptotic response. If you're interested in this kind of paper, there was a review article by, I don't know, a couple of years ago in Advances in Agronomy that deals with this type of model, and it's very useful for particularly for environmental and studies. But again, I'm not going to talk about it in detail, but you have the reference here if you are interested in them. So, and this is comes out of the Schabenberger and Pierce textbook, Sugarcane Yield in Response to Nitrogen Rates. They had six rates, and so we can have the rate constant, we can have the intercept, and we can call the ceiling, the estimate is slightly above our highest application rate. Did the study have enough rates? Yes, it did. The highest rate is probably not high enough. But then again, this study was done, the data is probably 50 years old. So now what you can do with, of course, with this model, you can't take an optimum, but you can say, okay, when do I, for example, have 90% of the maximum possible yield? So you can use it in all kind of further calculations. Now, I just listed here kind of the number of rates and that you can do here, but with a clear caveat, that for rate studies, you shouldn't use anything less than 4 rates. And so the more rates you have, you can do a lot of things. We can have, for example, here, get all these, we can in fact estimate a linear slope or a quadratic plateau model, do that. And software doesn't matter. You can do these kind of analysis. You can do it in SAS. You can do it in R. You can do it in JUMP. Whatever you have. Now, the limitation is there: can you model the residual variance appropriately if you have, for example, multi-site studies, or you have blocked studies? But that's a different question. Now, the rule of thumb in experiment design is, and this goes back to having enough replication. If you add another factor or another level, you get much more information than simply adding a replicate. The analogy is that replicates are to experiment design what sugar is in human nutrition. We need a basic amount, but in the end, complex carbohydrates, meaning additional factors or level, are much better. So what should you add? You can add additional level to better define the response curve. You can add year, location to broaden the scope of inference. You can add cultivar crop management to broaden the scope of inference. You can do irrigation and other fertilizer to broaden the scope of inference. The key take-home message, if you don't get anything else out of this talk today, is when you design this experiment, think multi-source regression, not traditional ANOVA when you plan your experiment. That is really the key take-home message. Now, Hans-Peter Piefu, whom I mentioned before, and Edmondson published this nice little paper, 7 years ago in Journal of Agronomy and Crop Science, where they had had this situation where you have quantitative factors in addition to qualitative factors. And then they developed kind of a stepwise approach. They have all the data, all the code is with there, so it's easy to follow. And like in my 7-step approach is you want to verify that the data is correct. It's what I call the giggle principle: garbage in, garbage out. If your data isn't any good, your conclusion can't be much better. And then you analyze it. If you have both quantitative and qualitative factors, analyze a classification experiment, graph the interaction treatment means, and then you develop the strategy for a multi-source regression analysis. And then you develop the most parsimonious regression model. You capture the regression parameters, you graph the predicted response to rate, and then you interpret the experiment and publish. And the interpretation, that's my last step in my 7-step approach, is of course very important. Doing the experiment itself and doing the analysis is not enough if you don't interpret and publish the data. And generally, we publish our data multiple times. A refereed publication is only one of those. It may be an EDIS publication in addition. It will be published at a conference where you present your data. It will be published at quote unquote published on field days where you talk to producers about your research. There are 2 books that can help you. This is quite old. This is almost 25 years old. But it's a step-by-step approach how to use those models, and they have an entire chapter on nonlinear models and regression models. It's based on SAS, but it's easily translated to R. The other one is to use this book by Ben Bolker, Ecological Models and Data in R. As the name indicates, it's based on R, but you can easily port that data to other software programs. But he does a nice job, particularly explaining the various nonlinear models that might help you. And when you have competing models, the simpler model is a better one, provided they have similar characteristic in terms of penalized fit statistic or the R squared if you're using that. Thank you, and that was the end of my run through to this introduction. So happy to respond to questions. And I believe Rebecca asked you to put your questions in a Q&A.
Nah, just in the chat. That's fine.
Okay. Okay, so Lakesh, you said since there's always variability in it, I learned from old professors not to normalize the data because of inflammation while develop nuclear recommendation. What do you mean by normalization?
So thank you, Dr. Van Santen, for this wonderful presentation. This is Lakesh. So when the data is not normal, so, you know, we run the normalization test on the data, and the data is not normal. What's your suggestion? Should we normalize the data, you know, log transformation?
Okay, that's what you mean by normalize the data. Okay, that's a slightly different. Okay. The data should be the first question you should ask yourself: what is a likely probability distribution that resulted in the body of data? For example, if you have yield measurements, we assume that they come from a normal distribution. Okay? When you see non-normal data, you look at the residuals, you don't look at the raw data. Okay? Think of this way: if you look at your raw data and you think they are non-normal, why should they be normal? You are applying, let's say you have 5 rates, you should actually have a mixture of 5 normals. Okay? Now, I have a talk on that. If you go back to the statistical, to our first Friday stat talks, I did a talk on that last year sometime. But anyway, you have a mixture of non-normal. What you're actually seeing there is not normality. You're seeing heterogeneity of variances. So what you do, that's why I said the first step is do the initial analysis, look at the residuals, and deal with the residuals. Often we can model the residuals. You don't want to transform the data. You don't transform the data because, for example, you mentioned the log transformation. When you log transform the raw data, you're not only transforming the mean response, but also the variance. You're automatically assuming a multiplicative relationship. Plus, the other thing is if you're doing a back transformation of the data, you don't derive the arithmetic mean, but the geometric mean. And the geometric mean is always smaller than the arithmetic mean. So it's really modeling the relationship appropriately. And both SAS and R have tools for that. So don't do it. Now, if you have count data, it would be on the same time, it would be a mistake to analyze those as if they are normal. No, count are discrete units, so they should be Poisson and negative binomial. Does that answer your question?
Perfect. So my next question is, sorry, I have a follow-up question. So so you mentioned about the one of the study that Lincoln Zottarelli did on the potatoes, and there was a range between 200 to all the way to 500 something nitrogen rate a requirement, and that is a confidence interval, right? That's the range that provides that optimum or the maximum yield somewhere.
Yeah, see this, for example, this study, what I have here, this is here's the join point here where there's no change, further change. And the confidence interval for this point ranges from 158 to 338.
Mhm.
It's so big to be meaningless, or
Gotcha.
less than helpful, we should say.
So what do you think, how small this should be? So when we say that this is good?
Okay, well, it depends on your pain threshold. I mean, I would say, okay, plus or minus 50 would probably work for me, but certainly having 150 pound range in the recommended rate, and you don't want to go above this because you don't get any point. But you could go as low as 158 statistically and get the same response.
Mhm.
Yeah.
Okay.
No, here definitely a rates would help. Probably one more, maybe two more.
Mhm.
Yeah, but really rates is where the number of rates is really the key to that. And the fewer you have, the more limited your interpretation is.
Thank you.
Okay, then. Okay, why the traditional is discouraged? Does regression replace the variance analysis? Well, nowadays we actually talk about linear models or linear mixed models, and regression is developing linear mixed models with a quantitative factor. If we treat it as a classification variable, it's also linear mixed models, but it's traditionally we would call that ANOVA. No, it doesn't replace it, but if you are my point here was when you do a rate study, you are really in the regression approach. The individual rates don't matter. It's the overall response that matters. And so can you develop a model that, say, if you have enough rate, if you can develop a quadratic model that you can define an optimum, if you have enough rates, can you do that? Enough rates also means that if you wanted to, you can have an optimum rate here, but if we add this rate here occurs in no man's land. It's nothing is even close to it. If we had another rate close to it and even another rate above the maximum applied, then we kind of had to have assurance that we are in the ballpark there. Does that answer the question?
Yes, thank you.
Okay, what SAS procedure to use to identify the inflection point for linear models? It's either proc NL, or I usually use proc NL mixed, because NL mixed enables you to incorporate random effects in the model, and then you can just write the formula to well, you can actually just set up the model. You estimate that inflection point, and both NL and LL mixed actually give you the confidence interval for that. It does an inverse prediction for you. Okay, but if you want to know, just stop by my office sometime and I'll show you. Okay, is there any R course or short workshop for faculty? I'm more a SAS person, but all my students use R. Yes. There are plenty of courses there. And Simon, are you still there? Raise your hand so people can see you. You may have.
Yep. No, I'm still here. Hi.
Yeah. There's Simon. You can tell them about what you did for the agronomy graduate students.
Yeah, the Agronomy Graduate Student Association asked me to give a talk on an R topic. I offered a couple of different options, and the one that people expressed interest in was nonlinear modeling for rate and dose response studies in agriculture. That one, I mean, that's already done. It was geared toward graduate students, but the basics are already there, and that could be pretty easily adapted. Yeah, you're welcome. That could probably be pretty easily adapted to a more advanced audience if that was something that people were interested in.
And just for information purposes, for anyone going to the agronomy meetings, I'm going to do an all-day workshop on analyzing complex data sets in using SAS. That'll be on Sunday from 8 a.m. to 5 p.m. I will also offer a SAS boot camp again in December. It's the week after classes. I will put out an announcement soon. And that will be 2 half days just for the basics of SAS or refresher. Any more questions? Okay. Okay, to follow up on the question for regression analysis, if a specific rate matters less than the trend, can we extrapolate outside the study rate? Who was that? Yogi Berra, I believe, said predictions about the predictions are perilous, particularly when they pertain about the future. This applies also for rate studies. The minute you go outside the range, your prediction error increases. Now you can see it here. Let me see. You can see it if you can eyeball it slightly. The prediction interval is smallest right at the mean rate here, and it gets tall. And as you go outside the rate, it blows up. And it depends because the prediction error depends on the Y error, but also on the difference between the average rate and the rate that you're looking at. Yeah, when you do a regression analysis, you want to identify the optimum rate. In this case, of course, we can't, because we haven't reached the limit. I'm not sure that you want to can justify more than 225 pounds. Probably someone would be coming down on you hard. But theoretically, we don't know where that response actually levels off. But if you have a curvature in the response, or you have some kind of a plateau model, then what really matters is that you say, okay, below this plateau model, let me do this one here. Below this plateau model, we can say here that for every unit increase in the nitrogen rate, we get 0.61 100weight or 61 pounds increase in yield. But that only goes up to here, and beyond this point, there is no further yield increase, so it levels off. But as I pointed out, and to do this again here, because of the experimental setup, this confidence limit for this joint point is so large to be practically useless. I mean, you can say it, but the experiment, it was just not designed well to do that. And by the way, this is, make sure, do you understand, this does not come from Dr. Zodarelli. I do not want to be nailed by Lincoln, okay? This is not his, this is some totally other data, okay?
Dr. Vincent, I have another question.
Yep.
So we had a nitrogen rate study, and you probably have seen that with Diego, Linto. And in that study, the maximum rate we had was 350 pounds of nitrogen per acre. We found that the quadratic model, we applied quadratic model, it was best fit compared to linear. So we found that it's still not plateauing anywhere, and it's still increasing. And so we add 450 because it was 70-pound interval. Sorry, 420 pounds. So 350, we put 70 more pounds, so 420. I haven't looked at the data, but we extrapolated try to understand what would be the maximum rate look like. And we found that till 900 pounds of nitrogen, the line's still not getting plateaued.
Yeah.
What's your thoughts on it? So would 420 be sufficient, the higher rate, or we should go beyond it?
It depends on what, I mean, 450 pounds, is that a one, I assume this is corn?
Yes.
And yeah, at one point, you guys just gotta stop. I know I've seen studies in forage grasses where Louisiana did one on annual ryegrass, that's probably 40 years ago, and they still hadn't leveled off at 500 pounds of nitrogen per acre. Yeah.
Okay.
But yeah, that you have to use your agronomic knowledge to say, okay, at one point we just got to quit. We can't do that. But of course, here then, if you have the linear increase, there's of course then an environmental cost that shows, assuming that the nitrogen use efficiency, what is it, 0.5?
It was very, very low. The increase was there, but it was not significant, obviously. But it was like in the form of like 1 bushel, half a bushel, then
Yeah.
a quarter of a bushel, 0.1 bushel. So it was that increase, but it was increasing.
Yeah, and at one point, but then you can another way to analyze the data is to convert the yield actually to net returns.
Yes, we did it. Yeah, we did.
And then you, but not overall, but calculate the net returns on a plot basis, and then just do a regular analysis on it.
Yeah, we
A
did.
lot of times people do these, ag economists do this on the basically on the average yield. No, you want to do it on a plot basis so you can do the statistical analysis, and then you can ask yourself the question: do the returns justify justify the increase? Of course, the higher the cost of nitrogen, that the cost of nitrogen will affect that.
We tried 2 different models. There, both are published in Midwestern states, and one is EONR, is called Economic Optimum Nitrogen Rate, and the other one is Maximum Return to Nitrogen, that's called MRTN. And we did apply that, and that basically give us the number that we're looking for. We also did the marginal return on it, and with the price of nitrogen and the price of bushel. So that helped to learn what that number could look like. But we are looking more a yield-based approach where we can convert, we can calculate how much nitrogen per pound you need to produce 1 bushel of corn when you have reached to a 0 margin return. And then you know, depending on each farm, because each farm is basically, it has its own yield potential. So each farmer can treat its farm site specifically and say that, okay, this farm is producing maximum like 220 bushels, then he can calculate how much nitrogen it needs versus 240 bushel farm yield potential. So we're kind of going to that approach, and that is more suitable to our area anyways.
Yeah.
Can I just, I've had a couple people message me to say that they would be interested in a workshop, an applied workshop on this in R. Could I just do like a quick poll? And if there's others who would be interested, could you message me to let me know, just so that I have a sense of how much interest there is? Thanks.
Okay, Travis has okay. And when measure the influence of sulfate from potassium sulfate, what is your recommendation to account for the influence of K when you have 5 rates of S and thus 5 rates of K? Yeah, the problem you have is the confounding. K and S are confounded. So in order to really solve that problem, you would really have to design a different study. But email me and email me your question and let me think about it rather than answering the top of my head. Okay, Travis, just email me that your question.
Thank you.
Okay, and then we just have. Yep. Okay, so next week, before we quit here, next week the Lincoln Zotorelli is going to kind of give a summary what's been done in at Florida, what in the various crops. He may emphasize his area of potatoes, but I asked him to look at all the studies and see how much in terms of the rates and so on. And then in November, we're going to have Alex Severinga. He is a graduate student at Iowa State, and he is going to talk about the problems that arise when you drop the zero rate, as it's often done in on-farm trials, or when you drop a rate that's close to the economically optimum rate. And there's consequences, and there's a price to pay. In other words, there ain't no free lunch. So you have to, somehow when you drop something, there's a price to pay. And then in December, the capstone will then be Hans-Peter Pifo from Hohenheim, talk about Bayesian approaches to designing rate studies to look at economically optimum rates. All right, I think we've covered everything, and I wish you all a good weekend. And then we'll meet again in a month. And this seminar is going to be on the in the Teams folder for the Statistics Consulting Unit, along with all the other talks we've done in this series.